Welcome back to BAS 120. We're going to talk about Chapter 6, Sampling and Estimating. So we're going to talk about how folks do statistical sampling. We're going to talk about the whole goal of it is to estimate what the population parameters are. We're going to talk about sampling error. Anytime we take a sample of something, inherently there's going to be an error. And how do we control that? We're going to talk about sampling distributions, confidence intervals, and how to determine a sample size that's appropriate. So let's talk about a sampling plan first of all. When folks do this, they're going to start off with what's the objective? What are we trying to do that accomplish? What's our target population? What population parameters are we trying to predict? What population frame or list from which a sample is selected? What's our method of sampling? Is it random or some other systematic way of sampling? What's our procedure to collect the sample data? And what statistical tools are we going to use? So these 6 elements all make up the part of our sampling or sampling plan. Let's talk for a moment about some sampling methods. We could do a random sample. That tends to be relatively inexpensive. We would just randomly select or use a random number generator. We could do a systematic. We could collect every 9th person or every 9th name in the telephone book, etc. We could begin to get, we could stratify our folks into different stratas and then take a percentage of that or a proportion of each strata to approximate our overall population, often done in, say, political campaigns where they'll stratify people into by age, by political party, and they'll sum them up based on a proportion of what they think the population is. Another example is a cluster. This is often used in, let's say I was introducing a new kind of burger at a fast food place. It probably wouldn't make economic sense for me to stratify and test market my burger all over the United States and in every single strata. So what I would do is I'd try to get a cluster that I think is somewhat representative of the United States. Columbus, Ohio happens to be a very famous test market because I can try my burger in that single cluster, and I know that cluster is very representative of the United States as a whole. The final type that we talk about is continuous process. So this is on production lines where I'm selecting, I'm taking a sample off of the production line to make sure that that batch or that production run is at the quality level I may desire. So those are the different sampling techniques. Now let's talk about what we're doing with the sample. The whole purpose of this sample is we're trying to estimate what the population parameters are. So we're taking this little sample here and we're trying to project what the population looks like. So our samples are called statistics. So the mean is represented by X bar, the standard deviation by a small s, and they're all being used to try to predict population parameters. So parameters talk about the population, statistics talk about the sample. So the parameter mean is mu and the standard deviation, different symbols, but the thing to remember is parameters are the population, statistics are the sample. Now, when we predict this population based on a sample, most likely we're going to be wrong. We're going to have some level of error. Now, there are different types of errors, and we need to understand those types of errors. 2 types of errors. First type of error, statistical error. That's where we're going to be off simply because we're not surveying the entire population. We're only surveying a sample. So statistically, we can calculate how much error we have by the fact that we're only surveying or asking a small subset of the population. This we have some control over because if we expand our sample size, we're going to have less and less statistical error. Non-statistical error is where our sample may just be a poor representation of the population. It may be biased. For example, maybe I did a campaign and I stratified, and I assumed that the strata of young people voters was going to be relatively small. And let's say in this election they turned out because they had maybe a popular candidate with young people. And my sample was biased. I underrepresented young people. Now, the reason that's normally unknown is normally I don't find out that my sample is biased until the election results come in. I find out what the population parameters are, because unless I'm biased myself or want my sample to be biased, I'm going to fix those biases if I know about them. If I knew that I was underrepresenting young people voter, I would have fixed it. So statistical error, I have some control over. Non-statistical error, you generally don't know about. Let's talk about a couple of things. It's important to understand this sampling error because it gives us additional information. This is just our point estimate, which we'll talk about. This is our point estimate of the mean. We think this candidate's going to get 53% of the vote. But this gives us our sampling error, or an estimate of our sampling error, which is equally an important piece of information. It's great to know that my candidate's getting 53% of the vote, but is the sampling error 1%? If so, I'm feeling very, very confident. Or if it's 10%, well, maybe not so confident. So both of these pieces of information are important to know. So how are we going to do this? How are we going to estimate this sampling error? Well, last chapter we talked about probability distributions. Now we're going to take it and we're going to take a sampling distribution. And if we know it's a sampling distribution, we can calculate how much error we have. So a couple of terms before we move forward. As I mentioned, back to our candidate example, this is a point estimate. This is an estimate of what the mean is. Very interesting, but it's also equally important to understand what our interval estimate is. How far off, how confident are we in that 53%? How much sampling error do we think we have? Now, when we talk about sampling distributions versus population distributions, we have a couple things working in our favor. First of all, there's a central limit theorem that basically says if the sample size is large enough, then the sampling distribution of the mean approximates a normally distribution of the population and has a mean equal to the population. This is one of the more important theorems within statistics. So, how are we going to estimate this standard error of the mean for our sample distribution? Well, our standard deviation of the means is going to be equal to the standard deviation divided by the square root of our sample size, because what is happening, if we think about this for a moment, if this is in the red or gray areas, our original distribution, if we do a distribution of samples, as our sample size increases, our variance or our standard error or our standard deviation is going to shrink by this as we increase our sample size. So if you think about this, an example might be, let's say our population mean is that the average height of men is 5'10". Now, the odds that I go out and select one person and they're 6'2" or taller is pretty good, because it's going to be somewhere in here. The odds that I go out and take a random sample of 64 people and those 64 men have an average height, that sample mean is 6'2", is very, very small. So my standard error of the means is going to shrink, become less and less and less variance as my sample size increases. Now, another way of saying less and less and less standard error is we become more and more and more confident in our prediction. Because if there's very little standard error or variance or standard deviation around our mean, then we're more confident in our prediction. So that leads us to what's a confidence interval. So a confidence interval is an interval estimate that provides a range for a population characteristic based on a sample. So a confidence interval can be 100 times 1 minus alpha percent is an interval from A to B such the population of falling between A and B is 1 minus alpha. 1 minus alpha is called the confidence interval. So some common confidence intervals are 90, 95, 99%. Confidence intervals are a way of assessing the accuracy of the point estimate. So let's talk about the confidence interval and how we calculate. And there are examples in the other videos where we go through in Excel exactly how to use Excel and how to use all the Excel tools to calculate all of this. But just to go through quickly, the confidence interval is the range. So we take our mean, in our prior example, our 53% votes, plus the z-score that corresponds to our alpha, times the standard deviation divided by the square root of n. Now this looks very complicated, but let's break it apart a little bit. So the confidence interval is x bar, which is basically our point estimate, our 53%, times our z-score of alpha divided by 2, which is a two-sided. So that basically is how accurate or how confident do you want to be? Do you want to be 99% confident? Do you want to be 95% confident? Do you want to be 90% confident? How confident do you want to be? How much sampling error can you live with? And this last piece over here, this standard deviation divided by the square root of n, is our standard error of the mean. So our confidence interval, and you're going to have statistical tools that'll do most of this for you in the videos on all the examples will walk you through that. But this equation you ought to have a degree of understanding on. Our confidence interval is our point estimate, our 53%. Plus or minus, how accurate do we want to be? What is our confidence interval? What is our confidence level? Times how much standard error, what is the standard error of the mean? So that's how the confidence interval works. Now, we have one minor problem in all of this. Everything we've been talking about so far is where we know what the population standard deviation is. We almost never know what the standard deviation of our population is. Because if we knew what the standard deviation of our population was, we probably wouldn't be doing the studies. So there's another family of distributions that have a wider variance than the normal distribution that we use extensively in statistics called the t-distribution. So the t-distribution is a family of probability distribution based upon how many degrees of freedom you have. And we'll go through degrees of freedom when we go through the examples. But, so you know how a t-distribution works and what it's for is, it's when we don't know this, we don't know the population standard deviation, which is almost always. So what we do is we say, you know what? We don't know what the standard deviation is. We don't know this equation. So what we're going to do is we're going to go and we're going to say, let's use what we do know. And what we do know, or we can calculate, is the standard deviation of our sample. Because we can take each one of our outcomes, compare it to our x bar, square it, and then rather than dividing by n, we divide by n minus 1. And that's just a statistical equation that makes sure we're unbiased, because we're adding a bit of unknown, because we're saying we don't know this, we're going to substitute this. So to compensate for that, we say n minus 1 rather than n. So in a t-distribution, the key things to remember is we're using the t-distribution when we don't know what our population standard deviation is. So we're going to say, let's take population standard deviation out because we don't know what it is, and let's substitute in our sample standard deviation. Now, The good news is a t-distribution. Here are some t-distributions as your n goes up becomes closer to a standard normal distribution. However, we are always going to use in this class the t-distribution every time we don't know what the population standard deviation is. Even though the t-distribution, as you get larger and larger n's, begins to approximate the standard normal distribution, we're going to use the t-distribution every time we don't know what the standard deviation of the population is. So a t-distribution is the same. Basically, the confidence interval for a t-distribution is very, very similar. We're going to use x bar as our point estimate. We're going to get a t-score rather than a z-score because we're now using the t-distribution. And we'll show you how to do that with all the tools. But it's the same thing. This is telling us how accurate do you want to be. And then we multiply this by our standard error. But in this case, because we don't know what the standard deviation of the population is, we're going to use instead the standard deviation of our sample. Now, one other problem we've got, what about proportions? What about where we don't have continuous? What about where we have success versus non-success proportions? We know, 60% of the time a person makes their foul shots or whatever. How are we going to get a confidence interval around success or failure proportions statistics? So we're going to use a slightly different equation, but it's still based on a lot of the same stuff. We're going to start with our p hat, which is our point estimate, our proportion estimate, plus or minus our standardized score, just like we did before. And we could show you how to get that in the table in all our examples, times, once again, the standard error of the mean. But this time the standard of the error of the mean looks a little bit different. It's the p hat times 1 minus the p hat divided by the n. And well, let's break this down and understand it a little bit. This standard error of the mean for a proportion is somewhat interesting. Let's think about this for a minute. If I ask you, whose outcome would you be more comfortable predicting? If I said to you, there's a 90% foul shooter going to the foul line, and your job is to predict whether that person's going to make it or miss it. I think most of us would say the 90% foul shooter is going to make it, and we feel fairly confident in that. Now, if I send up a 50% foul shooter and we had to predict, I think most of us would say, boy, that's tough. The guy is all over. Sometimes he makes it, sometimes he misses it. I don't know which. I'll predict he's going to make it, but I don't feel nearly as confident in the 50% foul shooter as I do in the 90% foul shooter. Well, note what's happening up here. Our p hat times 1 minus p hat for the 90% foul shooter is going to be 0.9 times 1 minus 0.9, which is 0.09, is our versus 0.5 versus 0.5, which is 0.25. So notice our standard error for somebody that's a 90% foul shooter is going to be a lot less than our standard error for somebody that's a 50% foul shooter. And I think that makes sense intuitively, because I'd rather try to forecast what a 90% foul shooter's outcome is going to be rather than a 50% foul shooter's. So that's just a little background on how this standard error for a proportion came about. So you've got confidence intervals for a normal distribution, which we often don't use because rarely do we know the standard deviation of a population. The ones we use most of the time is the confidence interval for a t-distribution and a confidence interval for a proportion, all of which we have several examples that we go through. Now, the last thing is we could, if you said to me, well, how big does my sample size have to be to do the confidence interval? Well, since we have these equations for all these things, it's simple algebra at this point to just, rather than solve for the confidence interval, we can do some plus and minus to both sides of the equation and solve for the sample size rather than the confidence interval. And again, there are a couple of examples in later videos that show you exactly how to do that. So, in conclusion, we've covered the importance of statistical sampling, how we use it to estimate the population parameters, different types of sampling errors, how we take a sampling distribution and use the central limit theorem to help us come up with confidence intervals. And we talked about confidence intervals for a normal distribution, for a t-distribution, and for parameters. And lastly, we can use this to estimate our sample size. Hope this helps. Any questions, let me know.